we will be making a sample ray casting simulation using Arkito. To start off, let's download the zip file for the Arkito repository on GitHub. Once it's downloaded, open it up and extract all the files from the zip file. Let's rename this folder Ray Casting Tutorial Video. Next, open up IntelliJ. Let's open up this project that we've downloaded. I've put it in my downloads folder. You can see right here, Ray Casting Tutorial Video. Let's open it up. You will trust this project. Let's wait for Gradle to build its model. Now that IntelliJ has fully indexed our project, let's open up the main folder, open up the source folder, and open up the game. We can delete all of these folders within the Arki game. These are all sample files. We will be creating our own app config. Let's create a new Java class. Call it Raycasting App Config. Let's add the app config annotation with the window title. We will call it Raycasting. A window width of 800, height of 800, and let's set resizable to false. Next, let's create our scene. You must create a scenes package in order to put it in the scenes package. And within the scenes package, let's create a new Java class called main scene. This is going to extend the scene abstract class. Let's import it. Within this abstract class, or within this main scene class, we are going to set it to the default scene, and we are going to set the background color to black. Next, let's create our start method and our update method and our render method. Our raycasting simulation will have to update the position of a few objects, including the raycaster. It will also have to be able to render supplemental objects. So we can just call the update scene game objects method that is already made into the Arkito game engine. This should handle all of that for us. Next, let's start creating our components. Let's create a new package called components. Let's create a simple component called a line bounds. This is going to extend the component class. The line bounds will have a public line2d called line, a public double slope. This is going to be the slope of the line. And we will actually be using the AWT line2d. Let's create a constructor. This constructor is going to take in the 2 points of the line, segment, it's going to take in the x1, the y1 for the first point, and the x2 and the y2 for the second point. Next, let's initialize our attributes, our variables, and let's add a render method. We are going to simply draw a line. Next, let's create a raycaster component. This is going to do the actual ray casting. And then we'll create a raycaster controller. This is simply going to allow us to move the raycaster around the screen as if it were a player. Before we get to the raycasting, let's create the line bounds prefab. Let's create a new package called prefabs. This should help us organize our project. Let's create a line prefab. This line prefab class will be a static class, and it will contain one method that returns a game object. It will take in the parameters of a line. These parameters represent the 2 points of a line segment, x1 and y1 for the first point, and x2 and y2 for the second point. We're going to return a generated prefab called line. It's going to take in a position of x1, y1, x2, y2, and an index of 0. Whoops. This won't take in a position, I just realized, because it is irrelevant to the line. Next, let's set up a size that is going to remain empty because we will be referring to the line's attributes through the line object itself, not the game object. The game object will simply be a container for the line, and it will be a container for the line bounds component. This will take in the 2 points that we pass through the parameters. Now we can go back to the main scene, and in our start method we can add a game object. We'll add the line prefab that we've created. Let's set it to 100, 300, 100. Let's run the program. You can see on it appears the black screen. We have forgotten in the line bounds when we render it to set the color to red. That way it will actually be visible. There we go. Alongside this line we can create some more lines. Let's add 3 more. We'll have 100, 100, 100, 200. And then we can set these to whatever values pleases us. I'm currently setting them to random values. When we run it, we should see random lines all over the screen. Next, we want to create a raycaster prefab. This will maintain the same format, relatively, of the line prefab. It's going to take in parameter distance, ray distance, and int the amount of rays. Let's import the GameObject class. And we're going to return a generated prefab called raycaster. It's going to be called raycaster. Now we're going to set its position, its initial position, to the middle of the screen. So this includes the app window dot width divided by 2 and the app window height divided by 2, and it's going to maintain a z-index of 0. Next, its size, we're going to give it a relatively small size of 8 by 8 pixels. Should be a 2 vector. Next, let's add a rectangle render. This component has already been created within the Arkito game engine. Let's set its color to red. We'll say, let's fill it. We'll add a new rigid body. That way we can actually move the object. And we'll add the raycaster component. This raycaster component will take in 2 parameters. It will take in the distance, the ray distance, and the amount of rays. So let's actually create this component. This component will have 2 different variables, both of which are final integers. These will be passed in through the constructor. And initialized there as well. Next, the raycaster will have an update method. It will also have 2 more methods. And let's return null for now. We will come back to these methods later. Okay, let's work on the math. I'm going to create a new package called raycastMath. And within this package, we are going to hold a static method called rcmath for raycastMath. And first, let's do a createRays method. This is a method that will take in the position of the player, or the raycaster in other words, the distance, the ray distance, the amount of rays we want to emanate from the player, and the color of the rays. Let's return null for now. In the meantime, let's create a public static line2d called create ray. We're going to take in, once again, the position of the raycaster or the player. We will also be taking in the ray distance as before, and the angle and the color. We will not be taking in, we will not be returning a list of rays, nor will we be taking in the amount of rays. Actually, the amount should be an integer. Okay. Now let's create two more methods. Public static double get side A, double angle, double ray distance. Public static double get side B, double angle, double ray distance. Now, to explain this, let's take a look at some math. This is all just trigonometry. All right, so if we do law of sines, or actually, rather, we will not be doing laws of sines. It will be a right triangle sine cosine tangent. If we look at these laws, let's take a look at this image. This is all we're doing. It's the SOHCAHTOA that we all learn in trigonometry. Right? Sine is equal to the opposite side of a triangle, the opposite side in relation to the angle, and the hypotenuse of a triangle. The cosine is the same, cosine of the angle is the same as the adjacent side to the angle, and the hypotenuse of the triangle. And we will not be using tangent. This is all simply to calculate the directions in which the rays will point, and therefore we shall calculate the different points, the end points to each ray that is coming from the origin, that is the player. So for get side B, we'll return the math.sine, and we're going to be taking in the angle as a degree, and the math, the Java math library uses radians, so we're going to convert it to radians. We'll pass in the angle, and we'll multiply it by the ray distance. This is the same as the sine law right here. Sine theta is equal to opposite over hypotenuse. However, in this case, the hypotenuse is the ray distance. Therefore, if we do sine theta equals to opposite over hypotenuse, we will multiply the equation by hypotenuse, and we get sine theta times hypotenuse equals to the opposite, which is the same as ray distance, the hypotenuse, times the sine of theta. That's the basis of the math we are using. Very basic trigonometry. Same thing with the law of cosines, just with cosine. We will be using these depending on which quadrant or rather not the quadrant, but we will be using it for the different coordinates of each point of a line segment. So in the create ray method, we will create a new line, a new 2D line, and we will create two vectors, a vector 2i called from, and a vector 2i called to. From is going to be a new vector that takes in the integer x and y, plain and simple, because this is the point that is coming from the origin player. Now the 2 is where the math happens. We create a new vector 2i. Let's move this aside so we can see everything better. This new vector 2i is going to take in the x and the y, and we will be creating x plus get side A. GitHub Copilot completed it for me, but just pause the video and type it out if you do not do not have time to type it. So what we are doing here is we're getting the side A of the triangle and side B of the triangle, and we're adding the y coordinate and the x coordinate to its appropriate coordinate value. This is so that when the player moves, the rays move with it. Now, in the line 2D, we can pass in the from, the to, the color, and the lifetime. Line 2D should, there we go. In the line 2D, we're going to have to create a brand new constructor. By the time this video is out, I am assuming that I will have updated the Arkito game engine to include this constructor automatically. In the meantime, let's create it from scratch. Public line 2D, vector 2i from, vector 2i2, and then we're going to pass in a color. We're also going to pass in a lifetime. So actually, let's copy this constructor. And instead of a vector 3, we're going to create a color. And the color will be set to a new vector 3f. Red, green, blue. There we go. So that will create our rays. Now we must create, or that will create our individual rays. Now let's create a collection of rays called rays, raw rays, is equal to a new array list. We're going to iterate through each index of the array list. And with each index, we're going to add a new array that we create. Let's delete these parameters. We're going to pass in the x, the y, the distance, ray distance, the angle. Now the angle is going to be equal to the index times 360 degrees divided by the amount of rays that there will be, and then we will pass in the color. Let's set this to a double. This says contents of, right, we have to return raw rays. Now, if you're confused as to what this is, think of it mathematically, right? Think of it as a pie. One full pie is worth 360. If we want to divide that pie worth 360 degrees into 4, then we're going to divide 360 degrees by 4. And that will get you the angle of one slice of pie. But let's say you want a specific slice of pie that is in, let's say, the third quadrant, then you multiply it by 3. Right, that's where this I comes in. If you want it, the one in the second quadrant, you multiply it by 2. I will be 2. If you want it in the fourth quadrant, you multiply it by 4, in which case I will be 4. Alright, now we can go back to the raycaster method, or raycaster component. Let's create a list called rays. going to be equal to rcmath.create raw rays. And we're going to pass in the screen position, the distance that we want the rays to be, the ray distance, and then the amount of days and rays, and then the color, let's set it to white. Each ray will be white. Now, we're going to have to create some additional methods within the RCMath class. Now, in this class, we're going to be calculating, or these additional methods, we're going to be calculating the intersecting point. What do I mean by this? Well, does Mac have a Paint program? I believe it does. Perhaps in Notes. Create new. Okay. Let me try to explain this. Let's say we have two lines. Okay, you can't really see that. Let's fill the color. Let's say you have line 1, which is green, and yeah, let's just have two lines both. Oh, okay, I guess this one's blue. Alright, so let's say we have two lines such as these two. Right, what this method should do is find the point where they intersect right in the middle. So that would be right here in this center, right here. We want to find this point. Our program currently knows the end points of each line segment. What does this mean? Well, it means I know this point. I know this point at the end of this blue one. I know this point at the other end of this blue one. I know this point at the end of this green line segment, and I know this point. However, we want to find the central point. So how do we calculate this? Well, we're going to use the line formula. So if we search up line formulas, you'll be able to see that there are three. We typically use the standard form, and this standard form can allow us to use a system of equations to isolate the point in which the lines intersect. That is what we will be doing. So let's create a public static point get intersect point int x1 int y1. This will be the first, or this will be the coordinates for at least one of the endpoints of the first line segment. And then we're just going to add the slope, pass in the slope of this line. Next, we're going to pass in the one coordinate of the second line segment. And then the slope of this line segment. Now before we do this, or actually, let's jump straight into it. Let's do a double. First we have to find the y-intercept. And this is the following equation. And then the y-intercept 2 for the other line. y2 minus m2 times x2. Now we're going to set up our variables that we will be returning. Let's just create that return statement, new point, right there. Alright, so first we have to check if the line is a vertical line. If it is, That means it's not going to have a slope, and our program will automatically set the double value to infinite, in which case we have to check if it's equal to infinite. If it is, we'll do x equals to x1 and y equals to m2 times x plus y-intercept 2. So if you recognize this formula, that's because it is very, very, very familiar. We learn it a lot in linear algebra. It's just the point slope form, or sorry, point slope form, I believe. Point slope form. No, it is not the point slope form. It is the y equals to mx plus b. Y equals to mx plus b. Why did it go to Yahoo? Y equals to mx plus... Oh no, I must have a virus. That is not good. Y... Oh wait, it's because I'm using Yahoo. I'm typing in y. Y equals to mx plus b. There we go. Right, slope-intercept form. There's a good picture to show it if you do not know the slope-intercept form. B is going to be the intercept, the y-intercept. So that is this yellow dot right here. This is where the line segment intersects with the x equals to 0 coordinate. And then the m is going to be the slope. And then there's y and x, which represents a point. That is the slope-intercept form. All right. Now let's do an else statement. Now we're checking if the second slope is undefined, or in this case, infinite. And we're going to do x equals to x2, y equals to m2 times x plus y-intercept. Actually, this should be 1, yes. M1 times x plus y-intercept 1. And then this third block, the else statement, will check if neither line is vertical, and so therefore calculate the intersect point regularly. So we're going to do x equals to y-intercept 2 minus y-intercept 1 over m1 minus m2. And then we're going to set y equals to m times x plus b. So m1 times x plus the y-intercept. And then we're going to return the point. We'll first cast the first argument into an int, and we'll do math.round x int math.round y. And there we go. We are all done. Now we just have to go back into the ray casting component. And let's finish off these methods. Let's first do the calc ray cast. We're going to iterate. In order to calculate a ray cast, we have to check if the ray is colliding with a line, with one of the lines that we have right here. One of these red lines. We have to check if our rays are going to collide with it. Right? So, to do this, we have to iterate through all the game objects in our scene. And we're just going to get all the game objects with the line bounds components. There we go. And let's call this lines. Let's now get a version of this line bounds component from each line that we iterate through. Line.getComponent line bounds.class. Next, let's check if these bounds intersect with line.getFrom or ray.getFrom.x, ray.getFrom.y, ray.get2.x is the second point on that line segment, ray.get2.y. And now we have to find the line slope, or rather the ray slope, so the double ray slope. Let's cast this to ray.get2, ray.get2.y minus ray.getFrom.y. So this is y2 minus y1 over x2 minus x1. That is the slope formula. Divide that by a double. It's going to be cast into a double. But it's going to be ray.get2.x minus ray.getFrom.x. So this is that x2 minus x1 part of the equation. Now let's create the endpoint. Get the intersect point. The endpoint is going to take in a few parameters. It's going to take in the ray's first point dot x, the ray's and then it's going to take in the slope, so the ray slope. It's also going to take in the first x, and then the first point y of the line, and then we're going to pass in the slope. And then we're going to set the line to a new line 2D. Let's delete these parameters. I'm going to pass in a new vector I. So right now we are passing in the 2 points of this line 2D. So we just passed in the from, now we're going to pass in the to. Now we're going to pass in the color and the lifetime of the ray. Actually, this should be ray. Now we're just going to return that ray. In the calc rays method, all we have to do is do everything in the calc raycast method just for a bunch of different rays. So we're going to pass in a list of line 2Ds. Call this raw rays dot, and we are just going to replace all of its contents with that of the contents returned by calc raycast. Now here all we have to do is do calc raycast rays, and we can use Arkito's graphics draw to add the rays. Let's add another method. so that we can more easily add all of these. We'll do graphics draw.lines.add all lines, and we're just going to pass in that lines list. There we go. Now let's run it. Shouldn't get any errors. That is good. Now let's actually create this prefab. Let's go back into the main scene. Add a new game object called raycaster. Prefab.create raycaster. Set the distance to 250 and we'll add 4 rays. Or actually, let's add 10 rays. Let's run it. And as you can see, we have our raycaster. And as you can see, these rays will collide with the red lines and stop it in its tracks. Now let's actually go to the raycaster controller. Let's add some controls so that we can move this around and see our work better. Let's create a reference to the rigid body just so that we can reference it when moving, and we'll instantiate, or not instantiate, we will assign this rigid body reference in the start method. There we go. And in the update method, we're just gonna use the controls. We'll do if the key manager is held A, then we'll do rigid body move X. We'll just say -1. And there we go. That should be our raycaster controller all done. Now if we go into the raycaster prefab, we just need to add it. Run this. And now we are able to move our guy. And you can see that the rays will interact just perfectly with the lines. Except, did you see that just there? You can see it glitches. This is a result of the horizontal lines intersecting with the horizontal rays. We need to fix that. Okay, so how do you fix that? Well, let's go back into the math. Scroll down, and it has to do with the get intersect point. So what we want to check for is if two lines, or if the array and a line overlap. So we'll do Boolean overlaps vertically. So if two vertical lines overlap, in other words, they have the same slope and they touch each other. So if the double dot is infinite, M1, the slope of the first line, and if the other slope is also infinite, and if these two lines have the same x positions, and if it overlaps horizontally, we're going to do something similar. We're going to check if the M1, if both slopes are 0, so if both lines are horizontal, and then check if they have the same y coordinate. If so, then that will basically define it as, hey, these two lines are horizontal and they are overlapping and touching each other. Okay, maybe I shouldn't phrase it that way, that sounds wrong, but you know what I mean. So if it overlaps vertically, we're just going to return a new point, x2, y2. And otherwise, we're going to return a new point, x1, y1. Now that should fix it. Perfect. And we don't have any problems. Now let's take a moment to fiddle around with some of the settings we have. We have the ray distance and the amount of rays. Let's increase the let's decrease the distance to 50. Let's run it, and you will see that the rays are a lot smaller. That is exactly what we wanted. Now let's say we have decently long rays, just like this, but let's say we want more of them. So we'll just do amount of rays, we'll put 100. Now you can see we have a lot of rays. Now it looks like a light source. And they still interact just fine with our lines. That is ray casting, folks. This is really cool. Alright. Oh, you know what? Screw it. Let's put 500. Might get a little laggy. Actually, let's make it look as solid as possible. Let's put 1,000. Okay, this definitely might be like, oh, not laggy yet. Anyways, this is what ray casting is. You could implement it in your game for like shadows, for example, but really this video was really just meant to show the possibilities with the Arkito game engine, and really just how easy it is to do all of this. And of course we can also just have 4 rays if that's what we want. And actually I'm noticing that the rays are not centered with the player. We can actually change this if we go into the raycaster components. You can see we do get screen position. If we get screen center position, I believe that should fix it. It does indeed. It does indeed. Now the rays are centered with the player. Very cool. That is your sample raycaster simulation with Arkito. I hope this has been helpful. See you guys in the next video.